Today we will study about crystal field theory. The crystal field theory was first proposed in 1929. We have seen that in VVT all the d orbitals are degenerate. Degenerate means they have same energy, right? But according to this theory, this all the d orbitals are not degenerate. That means they will split into different energy levels. So this crystal field theory was used to predict the electronic configuration of metal ion present in crystal. It has some assumptions. So according to this crystal field theory, all the coordination compounds are purely ionic in nature. That means there is no covalent character in this metal and ligand bond, and these ligands are considered as negative point charges since the metal ion is positively charged and the ligands are negatively charged or negative dipole. So they have an electrostatic interaction to form coordination compounds. So here we need the concept of d orbitals. So as we know, we have total 5 d orbitals, right? So we classified them in two categories. So what is the first? In the first categories, the lobes of orbitals are in axial position only. See, in dz square orbital, the lobes are in z-axis only, and in dx square minus y square orbital, the lobes are in x-axis as well as y-axis. So we call them as axial orbital. But in the second category, the lobes are not in axial position, right? So they are in between the axis. All the three orbitals, the lobes are in between the axes, so we call them as non-axial orbital. So what is the applications of crystal field theory in octahedral complex? We structure of octahedral complex, right? So if we consider a cube and in the center of the cube our metal ion is present, and the metal ion has all 5 d orbitals like this, and all the 6 ligands are present in each face center of the cube. So if we separately see the d orbitals, then we can easily understand. So here is our axial orbitals, and these are our non-axial orbitals. So here our metal ion is present in the center of the cube, and the ligands are present in each face center, right? So here two phenomena occur. One, our metal ion has highly positively charged nucleus, so it will attract the negatively charged or negative dipole of the ligand, right? And but at the same time, the d orbitals contains electrons, right? So there will be a electronic repulsion between the ligands and the d orbitals. So the extent of repulsion will be different depending upon from which directions the ligands are coming. So let's consider there is no ligands close to the metal ion. So all the orbitals of this metal ion will be degenerate. As the ligands coming close to the metal ion, it seems like they are spherically coming close to metal ion. So all the orbitals feels repulsion equally. So they will increase their energy equally. But when the ligands are in the phase center, it is clearly seen that the ligands actually comes in the axial positions. So here dz square and dx square minus y square feels more repulsion compared to these three orbitals, since the lobes pointing towards the ligand, so dz square and dx square minus y square will be higher in energy. Since these lobes are not pointing towards the ligand, so they will stabilize, they will have a lower energy compared to these two axial orbitals. Here is the splitted d orbitals in octahedral complex. So when there is no ligands, only the free metal ion is present, all the d orbitals are degenerate, that is they have same energy. As the ligands coming close to the metal ion, all the d orbitals will increase their energy in equal extent, but when the ligands are present in each face center of the cube, these ligands will split in two energy levels. One is Eg and another is T2Z. Eg means doubly degenerate and T2Z means triply degenerate. So these are the two axial orbitals that get repelled more compared to these are the three non-axial orbitals. So the axial orbitals will have higher in energy and the non-axial orbitals will have lower in energy. And the energy gap between them is called as crystal field splitting energy. We denote as del O and O for octahedral. Applications of crystal field theory in tetrahedral complex. We know how carbon tetrahedral complex looks like. So here is the structure of tetrahedral complex. So here it seems opposite, right? The ligands are coming through the corner of the cube. Through the corner of the cube. Let's first see in the axial orbitals. So these are two axial orbitals. Ligands are coming through this corner, but the axials are present like these. So are not they are not pointing towards the ligands, so they will not get repulsion comparing to these three orbitals, because these three orbitals are pointing towards the ligands more compared to the axial orbitals. So here in this case the non-axial orbitals will have higher in energy and the axial orbitals will have lower in energy, because non-axial orbitals pointing towards the ligands more comparing to the axial orbitals. So here is the splitted d orbitals of tetrahedral complex. So these are the non-axial orbitals we denote as T2, and these are the axial orbitals we denote as E. Since they are in tetrahedral complex there is no symmetry there, that is why here no Z term is present, and this energy gap between them is called as crystal field splitting energy for tetrahedral complex, and we denote as del T. Now we are going to compare the splitting energy of octahedral complex and tetrahedral complex. Since in the case of octahedral complex, the axial orbitals are exactly pointing towards the ligands, so their repulsion is greater compared to compared to in tetrahedral complex, where the non-axial orbitals are not exactly pointing towards the ligands like in octahedral complex. So they will get repulsion less compared to the octahedral complex. As a result, their splitting also will be less compared to octahedral complex. So this splitting energy is greater and this splitting energy is lesser. So here is the relation: delta tetrahedral is equal to 4 by 9 delta octahedral. That means delta octahedral has greater splitting energy. So now we are going to see the different cases of octahedral complex. See the splitting energy levels of octahedral complex, right? These are the splitting energy levels of octahedral complex. Let's suppose this is the z-axis, right? This is the z-axis. So these two ligands we are going to compress. So what happened when we compress it? So when we compress the ligands, that is we are pushing the ligands towards the metal center. As a result, the dz square orbital present in the metal will feel more repulsion because the ligands coming close to it. So the dz square orbital will be in higher energy compared to dx square minus y square orbital, right? So when we are pushing the ligands towards the metal center in z direction, in the xy direction the ligands coming outward. So as a result, the orbitals containing x and y term will be stabilized because they are they are going from the metal center. So, and all the d term orbitals will be in higher energy. So, the highest energy will be dz square orbitals because we are pushing ligands towards the metal center in z direction. So, the highest energy will be dz square. Then this will split because the dx square minus y square will stabilize, so it will have the lower energy, right? And this will again split because z term will feel more repulsion. So yeah, this dxz and yz will be in slightly higher in energy, and this dxy, since it contains x and y terms, so it will be stabilized, right? So now we do the opposite direction, right? Now we are pulling the ligands in z direction. Now we pulling the ligands in z direction like this. So what happen if we pull the ligands in z direction, going away from the metal center? So the dz square orbital present here will feel less repulsion compared to the x and y axis. So as a result, that these z square orbital will be stabilized. So two axial orbital will be splitted, right? So in this case, it will be it will be totally opposite. That means all the all the x and y term orbitals will be in higher energy, since ligands are going away from the metal center in in z direction. So z term orbital will be stabilized. See, these two orbitals is splitted, and the dz square term will be is stabilizing, and dx square minus y square term will be destabilized. And similar case in the dxy, yz, and zx. So the dxy term will be in higher energy, and dxz and yz orbital will be in lower energy. In the extreme case, if we remove, in the extreme case, if we remove one ligand from the metal complex in from z axis, then the dz square orbital will be highly stabilized compared to the dx square minus y square orbital and all other dx and y orbital. So the dz square orbital will be stabilized more, so it will come down to this, and dx square minus y square will be destabilized, so it will come up with this. So these are all again this dxy will have higher energy, and dxz and yz will have lower energy. So when we are removing both this ligand from the metal complex, then it will become a square planar complex. Since we are removing two ligands from the metal complex, there is no ligand present in z directions, right? So then the dz square orbital will be highly stabilized, and it will come down to that positions. So this will simply come down to that position, and this will come up with that position, and this dx square minus y square will be, orbital will be more higher in energy, that is this will be more destabilized, and this dxz and yz will be lower in energy. So these are all the cases of octahedral complexes. So from this theory, we can predict the magnetic and structural properties of a complex, as well as the stability of a metal complex we can explain through this theory. So that's all about today's. Thank you.